Hi everybody, welcome back. So today's topic of discussion is going to be approximation methods for rate determination. Okay, so we discussed that a complex reaction will happen in multiple steps. So if it happens in multiple steps, how do we express the rate of complex reactions? That is the topic of today's discussion. Very important topic. A lot of questions have been asked in several competitive examinations. Before moving to the topic, let's discuss the answer to one homework question which was given. Correct? So this was the question which was given. Consider a reversible reaction. This is where A becomes B with the rate constant of K1 and B becomes A with the rate constant of K2. They have given that if A, X, Xe are initial concentrations of A, concentrations of B at any time T, and the equilibrium concentrations of B respectively, then dx by dt is. So we need to understand each and every term in order to solve this. Correct? So what is our equation which is given? A giving B. Forward rate constant K1, backward rate constant K2. At T is equal to 0, initial concentration, it is given that it was A. At some time T, we can write that A minus X is the amount of the reactant left and X is the amount of product formed. While when the time reaches equilibrium, it can be written as A minus Xe and the amount of product formed is Xe. Correct. We know that the net rate at any time can be written as rate of forward reaction minus the rate of backward reaction. Now, forward reaction is A giving B, and at any time, the concentration of the reactant is A minus X for the forward reaction. We have already derived it. I'm not repeating it. So it is going to be rate constant of the forward reaction, or let's write it as K1. K1 into A minus X. And for the backward reaction, B gives A, it is K2 into concentration of B at any time is X. Right. So this is the net rate. And if I have to write for the reaction A giving B, theoretical rate can be written as minus dA by dt is equal to dB by dt. And what is dB by dt equal to? dB by dt is equal to dx by dt, and that is the question. In the question, they have asked us to write the expression for dx by dt. But you can see that among the options, you have Xe in it. You have Xe in it. And the only rate constant which is present is K1. But in the expression of dx by dt that we have, there is only X and there is K2. So we need to eliminate K2 and we need to introduce Xe. Correct? So what will we do? We will write the net rate at equilibrium. The net rate at T equilibrium we'll write. What is that? That is also Rf minus Rb, but that is going to be equal to 0. Correct? So at equilibrium, what are the changes? dx by dt will become equal to K1 into A minus Xe, which is the concentration of A at equilibrium, minus K2 into Xe, which is the concentration of the product at equilibrium. Huh? Now we can see from the options that there is no K2. In none of the options there is K2. So we need to eliminate K2. And at equilibrium, this is equal to 0. So let's take this and substitute for K2. K1A minus Xe is equal to K2Xe, or I can write K1A minus Xe by XE is equal to K2. So I have got an expression for K2. I'll put this expression of K2 in 1. Label this as 1. Where you have written the net rate at any time. Where you had K1 into A minus X minus K2 X is the net rate. So there is K2 over here. We have found an expression for K2. Substitute. Let's substitute. So what do you get? Put 2 in 1. Dx by dt is equal to K1 into A minus X minus, it is K2 into X. We need to substitute over here, right? So K1 A minus X minus K1 into A minus XE divided by XE into X. So this highlighted portion is the substitution for K2. Open the brackets and cross multiply. K1 A minus X minus, open the brackets, K1 AX minus K1 XEX. This minus and this minus becomes plus divided by XE. Cross multiply again. K1 AXE minus K1 XXE minus K1 AX plus K1 XEX divided by XE is dx by dt. This is plus K1 XEX. This is minus K1 XEX. That gets cancelled. So you get dx by dt is equal to K1A by XE is common. And in the bracket, what you have is XE minus X. This is the expression for the product formation. Let's look at the options. K1X by K1A by XC into XE minus X. Option C is the correct answer. You will be only able to do this if you're thorough with the concept of derivation. Okay. All right. Now, write down the heading, approximation methods. Approximation methods. Why are approximation methods used, first of all? Approximation methods are used to determine the rate expression for complex reactions. For complex reactions. Okay. Now, the key of the approximation method, the major key, the major concept that you should know is in the complex reactions, the slowest step, very, very, very important. The slowest step. So we said there are multiple steps in complex reactions, and among them, the slowest step is the rate determining step. Rate determining step used to write the expression of rate. Important. The slowest step is used for the rate determination. So I was thinking about giving you a conventional example so that you can understand this concept of slowest step. So you might have had a time where you sit with your colleagues and have lunch. Hmm? And let's say it's a group of 4 or 5. And you sit there even after if you have completed your lunch until the slowest person in the group completes having his or her lunch. Correct? Now, let's say we are a gang and I'm a slow eater. So, even though you have finished your lunch, you will wait until I have finished my lunch so that we can go together and then wash our hands, etc., etc. So, I am the slowest eater in our gang, and I determine the speed with which we get up after our lunch. So, it depends on the slowest person. Okay. So the slower the person is, today, let's say I took 45 minutes to complete my lunch. All of you will be taking 45 minutes to go to the washroom and wash your hands. But let's say I'm who the slowest. I take only 30 minutes. Then our lunch ka thing is over within 30 minutes. Okay. So the slowest person determines the speed of completing the lunch time. Similarly, in complex reaction, the slowest step is the rate determining step. Okay. Now, another thing, so that is one point. Another point is in rate expressions, you note it down. Rate expressions must only contain stable species. Very important. Must contain only stable species. Stable. What are stable species? Stable species. Stable species. Or in other words, we can say that in rate expressions, you note that down as well. Rate expressions will not have intermediates. What do you mean by that? For example, take a hypothetical example. Let's say I have A plus B, which forms some intermediate I with a rate constant of K1. Okay. And this I further becomes products with a rate constant of K2. And it is given in the question that this is the slowest step, let's say. So according to rule number 1, the slowest step determines the rate determining step. So here, if we have step 1, we have step 2. Step 2 is the rate determining step. So from the rate determining step, we can write the expression as R is equal to rate constant of that step into the reactant of that step, which is I. And this is not allowed. Why? Because you can see A plus B is our reactant, which becomes some intermediate, and that intermediate further breaks down to some sort of products. So having intermediates in the rate expression is not allowed. To eliminate the presence of I in the rate expression, we need approximations. To eliminate I from the expression, which is the intermediates concentration, from the expression, we need approximations. Okay, we need approximations. There are two approximation methods. First one though is very easy. Second one will become easy with practice. Okay. So write down the first heading, approximation method. The first type is equilibrium method. Equilibrium method. We will be understanding the methods with proper questions. Equilibrium method. Equilibrium method. Directly note down a question. Slash number 46. Okay. Suppose that expression is given 2O3 ozone becomes O2. This is the overall reaction. And they say that this happens in two steps. This happens in two steps, and the two steps are O3 has an equilibrium with the formation of O2 plus O, and it is given in the bracket that this is fast. And in the next step, O again with O3 gives us 2O2. And it is said that this is slow. It happens with the rate constant of K3. This is the question. And you have to find the rate expression using the approximation of equilibrium method. Using the approximation of equilibrium method. Okay. So first rule, slowest step is the rate determining step. Slowest step is the rate determining step. So let's see who the slowest step is. Step number 2. If step number 2 is the slowest step, we write that rate is equal to, this is the slowest step, correct? O plus O3 giving 2O2 is the slowest step. So if you have to write the expression, we said that this is a complex reaction which happens in two steps. Each step is going to be elementary. That is also something that we know. And now we know that the elementary step, which is the slowest, is the rate determining step, RDS. Now, if we know the rate determining step, we can write the expression for rate. Rate is equal to K3 into concentration of O into concentration of O3. Since they are elementary, you can put their powers same as the stoichiometry. Correct. Now, if you look at this expression, O3 is something which is there in the reactant. O3 is a reactant. And that is stable. The reactants and products are stable. All those species which are not part of the reactant and the products are called intermediates. For example, you have O over here. O is over here as well. It's not there in the reactant side. It's not there on the product hand side. So this is the intermediate that we have to rule out. This is the intermediate that you have to rule out. And if you have to rule out that intermediate, you need the method of equilibrium. Now that is very easy. Which is the equilibrium step over here? The first one. Correct? So from step 1, we will write the expression for the equilibrium coefficient. Or, you note down from Step 1. What is step 1? O3 becoming O2 plus O as it is an equilibrium. You can write the equilibrium constant. What is the equilibrium constant? Forward rate constant divided by backward rate constant. And that is equal to product concentrations divided by reactant concentration. This is how you write the equilibrium. Concentration of the products of the step. What are the products of the step? O2 and O divided by the concentration of the reactant, which is O3. Okay, so for any reaction, A plus B giving C plus D, the equilibrium constant, which is equal to the rate constant of the forward reaction divided by the rate constant of the backward reaction. If you want, we'll write that. K1, K2. K1 by K2 is equal to concentration of the products. You take the product of that and divided by the products of the concentrations of the reactant. Okay, raised to their stoichiometry. Here the stoichiometries are all 1. That's it. Now from this, you can rearrange the expression for O. You can keep O, which is our intermediate on one side, and it can be written as K1, K2, concentration of O3 divided by O2, correct? When you rearrange, you'll get this expression. Now you will use this and you will put this in the rate determining step. Or if this is 1, you will put this in 1. Put the expression of the intermediate O in 1. So what do you get? R is equal to K3 into K1 by K2, concentration of O3 by O2 into, there is already a O3 in the expression. Or I can write R is equal to K3 K1 by K2 into concentration of O3 to the power 2, concentration of O2 to the power minus 1. This is the rate expression for the complex reaction which was given and approximated using equilibrium method. Very easy. You wrote the rate expression using the slowest step. There was an intermediate. We need to remove that intermediate using equilibrium coefficient, and you just put it over here. That's it. Very easy. You will get more questions in the assignment. So if they ask you the effective rate constant, how will you write? Rate is equal to effective rate constant into concentration of O3 to the power 2, concentration of O2 to the power minus 1. And thus K effective, that is equal to K3, K1 by K2. What is the total order of the reaction? Total order of the reaction. Total order of the reaction is 2 with respect to ozone minus 1 with respect to O2. So total order is 2 minus 1, 1. Total order is 1. I hope it is clear. You have only the expressions of the reactant O3 and the product O2, both of which are stable. Both of these are stable. O3 is the reactant, that is stable. O2 is the product, that is also stable. So you can have stable components in your rate expression. Even if O2 is a product, that's fine. Products can be there. But you should not have intermediates. You should not have intermediates. I hope you understand what are intermediates. What are intermediates? Let's say you take these two and you add them up. You add them. So when you add them, A plus B plus I on the left gives I plus P on the right. I and I gets cancelled. So intermediates are those which does not appear in the overall reaction. So let's say our overall reaction, this was our overall reaction where we have only O3 and O2, correct? So those candidates can be there in the rate expression, but not anyone other than O3 and O2. This is the equilibrium method. Very easy. You'll get more questions in the assignment, okay? Okay. Next one. Next method is something called steady state approximation. Steady state approximation. Before going into the steady state approximations, I will like to discuss certain forms of graphs. Okay. So only a particular category of reactions can be used for steady state approximations. And what are those? Let's see. In the previous session, we discussed about consecutive reactions, where A becomes some intermediate I and later on it becomes product. So this is our intermediate. So for the formation of the intermediate, there is a rate constant K1, and for the formation of the product, there is a rate constant K2. Now, depending on the relative speeds or the values of the rate constants. So yesterday we took A, B, and C. I'll proceed with the same or in the previous session. So here B is our intermediate, okay? Intermediate. Now let's discuss certain graphs. So case 1 is where K1, the value of K1 is way higher than K2. Value of K1 is higher than K2, meaning A gives B whose value is very high and this is fast. Large value of rate constant means it's quick. While B becoming C is slow. So if I had to draw the graphical representation for this. So here I have concentration of my species. Here I have time. So first one is A. We have already learned the expressions of A, B, and C with time yesterday. It all showed exponential decay and exponential increase from the expressions. So A, you can see that A giving B is very fast, meaning A disappears fast. If you want to write, please note it down. As K1 is high, concentration of A decreases quickly. And that happens exponentially as well. Why exponentially? Why? Because concentration of A was equal to A naught e to the power minus K1 into T. Discussed in the previous session, revise. Okay. So A will decrease like this quickly. This is concentration of A. What about B? B also had exponential terms in it. And as it is an intermediate, what you can see, in step 1, which is the fast step, B is being formed. Here, B is being formed. And that happens quickly. While in the second step, where disappearance of B is there, that is slow. Okay, so if you want to write, please note it down. As K1 is larger than K2, intermediate B appears quickly and disappears slowly. Correct. So it forms quickly while disappears slowly. So how will the graph look like? So it forms quickly, but then degrades slowly. It's a slow decrease. So green color trace over here shows the concentration of B. There is a tip point over here where this is the maximum concentration of B, and the time corresponding to the formation of maximum concentration of the intermediate is T max, and we know the expression for the same from the previous expression, right? Ln of K2 minus ln of K1 by K2 minus K1. Okay. And from the expression again, C, which is the final product, is formed slowly as K2 is very low. Concentration of C or the product C is formed slowly. This is formed very slowly. So if we have to show it slowly, slowly only it will increase. So this is C. Okay. This is case 1. This is case 1. Understand the graphs. There have been questions which were asked. Now case 2, the opposite. Case 2, where K2 is much, much higher than K1. Meaning A gives B with a rate constant of K1, that is slow. And B giving C, the product formation is fast. We need to plot a graph for this. Let's try. So we have concentration of the species along y-axis, time along x-axis. What can we see? In first step, where A is being disappeared, it is happening slowly. Slowly. So the disappearance of A, which happens in first step, happens slowly. So A disappears slowly. Slowly. So earlier we saw that it disappeared quickly. Here it disappears slowly, slowly. Earlier when it was quicker, it was very close to the y-axis like this. This is the case when it is quick. So when it is slow, it is farther away from the axis. It is a slow decrease. Okay. Now what about the intermediate? What about the intermediate? So intermediate B is formed very slowly in first step. But the moment it is formed, it quickly gets converted to the product. Okay. So B formation is very slow, but it disappears very fast. So you can write as K2 is way higher than K1, the intermediate B appears very slowly, but disappears quickly. Disappears quickly. Meaning, the way you will draw it is, it forms very slowly, but the moment it is formed, it will disappear. The moment it is formed, it will disappear. Okay. So it won't be this slanting as well. The moment it forms, it disappears. It will form, it will disappear. It will form, it will disappear. It will form, it will disappear. It is slightly slanting. It's not even straight, slightly slanting. Very slightly slanting. And this corresponds to the concentration of B. I hope this concept is clear. The moment you form B, immediately it is disappearing. That's why here there is no rise in the concentration of B. There is no rise. Because the moment it is formed, it will disappear. The moment it is formed, it will disappear. It will disappear into what? It will disappear into the formation of C. Correct? So, because C formation happens with the rate constant of K2, and that is very high, the step is very fast. Product C forms quickly, very fast, very fast. So it forms quickly like this. Now, such conditions where the rate constant of K2 is greater than K1 is where you can apply the steady state approximation SSA. Very important. Highlight, mark it as very important. These are the only conditions where you can apply the steady state approximation. That is a heading, SSA. What is steady state approximation? Steady state approximation is you look at the graph corresponding to B, where the moment B is formed, it disappears. The moment it forms, it disappears. And when the actual data is plotted graphically, we can see that it is almost linear. Almost linear, not exactly linear, almost linear. So if you take the slope at any point of this B, you can see that what is slope? It is a derivative at this point. So di, or it is B over here, dB by dt is equal to 0. Correct? Because it is almost linear. Why is it linear? The moment B is formed, it is disappearing. It does not have time to increase at all. Does not have time to increase. Okay. So this is the conditions of SSA, where the intermediate is formed quickly. Sorry, the intermediate is formed slowly but disappears quickly. And corresponding to the intermediate, you can put these conditions of dB by dt, which is the changes of the concentrations of the intermediate with time as equal to 0. This is the heart of steady state approximations. There has been questions where you can apply SSA. Understand, you can apply SSA only when K2 is greater than K1 and not in any other conditions. Not in case 1, only in this case. There's one more condition, K1 equal to K2. K1 approximately equal to K2. Plot it on your own. Now you know the concept. Try. Concentration of species. Time along x-axis. We have 2 steps. A giving B. Rate constant is K1 and B giving C. Product formation. Concentration of A degrades with time. Concentration of B appears with a speed and concentrations of B disappears with the same speed. Concentrations of B appears and disappears with same speed. Because K1 and K2 are same, so if you have to plot it, you can plot it like it forms with a speed and degrades with the same speed. Almost same slopes on both sides. One is increasing and the other one is decreasing. This is concentrations of B. And for C, it is being formed. That's it. You can show it like this. C. Okay. All right. So what we want to focus upon is case 2, where we can apply the approximation. And what is the approximation? Approximation is as the concentration of B attains steadiness after a certain while. How does it attain the steadiness? Because the moment it is formed, it disappears. The moment it is formed, it disappears to the product. And that is the conditions of steady state approximation. Understand the steady state approximation can be applied only on the intermediate. SSA can be applied only on intermediates, not on the reactants, not on the products. Okay? So the moment the intermediate is formed, even though very slowly, it disappears quickly. Okay. So the same question, that is question number 46 we did. We'll take the same model reaction and let's try. 47. This is 46, right? 47. What was the overall reaction? Overall reaction was 2O2 giving, 2O3 giving O2. And step 1 of the complex reaction was one second. Let's break it down, okay? Step 1 was O3 giving O2 plus O. This is an equilibrium process. I'm just splitting it so that you can get it easily. Step 2 is the reversible one. O2 plus O becomes O3. And step 3 is O plus O3 giving 2O2. And this happens with the rate constant of K3. One second. Please let me cross-check the question. Okay. Just a second. All right. So there's a correction in the question. There are only 2 steps given. Sorry, there's only 2 steps. Okay. So step 1 is O3 giving O2 plus O with a rate constant of K1. And step 2 is O3 plus O becoming 2O2 with a rate constant of K2. Okay. Depending on the question, they'll change the mechanism. Don't worry, the mechanism will be given to you. Now they have asked us to find the rate expression. Find the rate expression using SSA. SSA is steady state approximation. Okay, one thing. Here in this question, they have not given the slowest step. Okay, they have not mentioned whether step 1 or step 2 is the slowest step. Unless and until we know the slowest step, we cannot determining the RDS, the rate determining step. So note, if RDS, which is the slowest step, is not mentioned, the step corresponding to product formation, the step corresponding to the product formation is used for determining the rate. Okay? Please understand that in the earlier question, there was a clear mentioning about the slowest step. See, they had mentioned that this is the slowest step. Let's say that they don't mention, it's okay. Always take the step where the product is being formed. Who is our product? O2 is our product. So this is the product formation ka step, and we'll be using that for writing the expression of the rate. Okay. So from here, step 2 is the rate determining step, as that is a step where the product is being formed. So R is equal to K2 into concentration of O3 into concentration of O. Now, O3, look at the overall reaction. O3 is something that we have on the reactant side, and that is stable. But O is not something that we have in the overall reaction. So that is the intermediate, and we have to eliminate the intermediate. We have to eliminate the intermediate. How do we eliminate the intermediate? So in order to eliminate the intermediate over here, note it down. This one is our intermediate. And they have said that we have to use SSA. And in SSA, what is the approximation that we take? Using SSA, the changes of the concentrations of the intermediate with time can be taken as 0. We already saw the graph. So here, who is the intermediate? Changes in the concentration of O with time is put as equal to 0. We'll be using this equation. So we need to know how is the concentration of O changing. So let's look. Let's take these 2 equations. Note it down. Take these 2 equations. Pay attention, please. So in the first step, we need dO by dt, okay? So in the first step, O is being formed. So dO by dt being a product, and as it is being formed, we can write the rate corresponding to this as K1 into concentration of O3. Because this is elementary, and you can write this expression, K1 into O3. In the second step, O is disappearing. O is disappearing. So as it is disappearing, you need to put minus because it is on the reactant side. So minus dO by dt is equal to K2 into concentration of O into concentration of O3. Correct. Now for SSA, you need dO by dt. So from the first step, you have dO by dt. From the second step, you have minus dO by dt. So make it plus. You take the minus to the other side. dO by dt is equal to minus K2 concentrations of O into O3. I hope you understood how this minus came to the other side. Because it is disappearing, you can write the rates of disappearances only, and we rearrange it to get dO by dt. That's it. So you have two expressions. We will add them. Correct? So the total dO by dt is from the first step, it is being formed. K1 concentrations of O3. In the next step, it is disappearing. So minus K2 O into O3, and this is equal to 0 using SSA. This is 0. So use this and rearrange. So K1 concentrations of O3 is equal to K2 concentrations of O into O3. Keep O on one side. K1O3 divided by K2O3 is equal to concentrations of O. O3 gets cancelled. I can write O as equal to K1 by K2. Now put this expression of O over here in the rate expression. Let's say this is 1. Put it over there. Put 2 in 1. We are eliminating the intermediate and we have got an expression for intermediate. So R was equal to K2 concentration of O3 into O. We will put this over here. And that becomes K2 O3 into K1 by K2. No need of brackets. So K2 gets cancelled. Overall rate is equal to K1 into O3. That's it. Please pay attention. I'll repeat this question once again. In the mechanism, it was not mentioned that which step is the slowest. So if it is not mentioned, if it is mentioned, it's very easy. You will take that step, write the expression and go on. Here it was not mentioned. We'll take the step corresponding to the product formation as the rate determining step. We'll write the expression. We found who the intermediate is and we have to remove the intermediate by SSA. SSA is putting this condition of changes of the concentrations of the intermediate with time as equal to 0. How do you do that? Take the individual step, write the expressions, add them, put it equal to 0, rearrange them and substitute. Very easy. Let's do a few questions so that you get a good practice. Question number 48. Question number 48. Very easy, yeah? The question given is A plus B gives C with a rate constant of K1 and C gives D with a rate constant of K2. It's given in the question that this is the slowest step. And the question is to find the overall rate expression. Overall rate expression. Okay. First of all, it does not have any equilibrium, so we cannot use the approximation method with equilibrium. We will have to proceed with SSA. Okay. Now to identify who the intermediate is, it's very easy. You just add them. Try adding them. If you cannot identify, you should be able to identify in one go. Let's say I add them. A plus B plus C gives C plus D. C gets cancelled. So my overall reaction is A plus B giving D. This is my overall reaction. So A, B, and D are stable, while C is the intermediate over here. Okay. So now you have identified who the intermediate is. Intermediate is C. Okay. Also, they have given who the slowest step is. Step 2 is the slowest step. So rate is equal to rate constant into the reactance of the slowest step, which is C. Put this as equation number 1. Now, as we have to eliminate the presence of any intermediates and there is no equilibrium, you will have to apply SSA. And what is SSA? Using SSA, we know that the changes in the concentration of the intermediate with time is equal to 0. So let's find that out. Now we won't be writing step by step. We know the concept. So we need to know the formations and the disappearances of C. Okay. In first step, it is being formed. In first step, it is being formed. So it is plus because it is being formed. K1, the reactants are A into B. In the next step, it is being disappeared. It is disappearing. So minus K2 into C. Correct. And this is equal to 0. From steady state approximation, this is equal to 0. So when you rearrange, K1 concentration of A into concentration of B is equal to K2 into concentration of C. And concentration of C is equal to K1 A into B by K2. This is equation number 2. We have found the expression for the intermediate. Put it over here. So put 2 in 1. What do you get? R is equal to K2, K1, concentration of A into B divided by K2. K2 is cancelled. So the overall expression is K1, concentration of A into concentration of B. Who is the effective or what is the effective rate constant? K1. What is the total order of the reaction? 1 plus 1, 2. This is how you solve the question. Once again, one more question. 49. 49. The question is A plus B in equilibrium gives K1, K inverse gives C, and C plus D gives P, and this happens with K2 rate constant. Question is to find the overall rate expression A. B is to find the order when concentration of, one second, concentration of D is very high. Sub-question C is order when concentration of D is very less. Okay, very important. Overall rate expression using SSA. Using SSA. Okay. So even though there is an equilibrium over here, they have asked us to find the expression using SSA. Again, the slowest step is not given. Usually equilibriums are very fast. Okay. So keeping that aside, again, it is not given. So our rate determining step will be step 2. This one where product is being formed. Identify who the intermediate is. Identify who the intermediate is. So when I take the overall reaction, A plus B plus C plus D on the left gives C plus P. So C gets cancelled. A, B, D and P are stable. C is not there in the final expression. So C is the intermediate. This is how you identify. Okay. Now that you have identified, what is the rate expression? Rate expression is equal to K2 into concentration of C into concentration of D. But as C is the intermediate, we'll need to remove this by SSA because it's already given that we have to remove it by SSA. Understand that there are 3 steps, not 2. There are 3 steps. What are the steps? A plus B giving C. Reversible one. This happens with K1. The ulta, C giving A plus B, which is K inverse. And the last step, C plus D giving P, which happens with K2. So if we have to apply SSA, the derivative of the intermediate with time is going to be equal to 0. So find the expressions for all of these. So let's write it as a totality. dC by dt. In first step, it is being formed. So plus K1 concentration of A into concentration of B. In the next step, it is being deformed. So it's going to be minus K inverse. Who's the reactant? C is the reactant. In the last step also, it is disappearing. So again, minus K2 concentration of C into concentration of D. This is going to be equal to 0. Rearrange and find the expression for C. Let's say this is 1. Rearrange. So after rearranging, K1 concentration of A into B is equal to K inverse C plus K2 C into D. I'll take C outside and rearrange. Concentration of C is equal to K1 concentration of A into concentration of B divided by K inverse plus K2 into D. This is my expression for C. I put 2 in 1. And there I get my answer to the first sub-question. When I put C in 1, what do I get? I get already K2 into D is there. Already K2 into D is there. And now I have to write the expression for C, which is K1 concentration of A into concentration of B divided by K inverse plus K2 into D. This is the expression for rate considering C as the intermediate and using the method of approximation SSA. Right? So we got that. Now what is the next sub question? What is the order when the concentration of D is very high? Okay. Now see two sub question B and C And they have asked us to put the conditions where the concentration of D is very high. And here the concentration of D is very less. Why? Because, see, here you cannot determine the order because the expression is too complex. Okay, so here with respect to D on the numerator it is 1, with respect to A it's 1, with respect to B it's 1. But at the bottom again there is some constant plus K2 into again D. So to determine the order it's very difficult as there is a plus sign at the denominator. So they have given two conditions. First condition is when D is very high. So if D is very high, you'll always look at the denominators, okay? When such conditions are given, you always look at the denominators only. So if D is very high, K2 into D will be very high than that of K minus 1 because D is high. The product of K2 and D also will be high. So from the expression, you can write rate as equal to K1, K2, concentration of D into concentration of A into concentration of B divided by K2 into D. You can neglect K minus 1 because it is very small. Doesn't matter if it is there or not. So you just neglect it. After neglecting K2, K2 gets cancelled, D gets cancelled. So the expression is K1 A into B. What is the total order? Order when the concentration of D is very high is equal to 2. Okay. Next, they are saying that the concentration of D is very less. If the concentration of D is very less, K2 into D will be very less than that of K inverse. So whoever is less can be neglected. So when that is neglected, it becomes K1, K2, D, A, B divided by K inverse because K2D is neglected. So what is the total order? Order is 1 plus 1 plus 1, 3. And what is effective rate constant? It is K1, K2 divided by K inverse. Okay. Last question will be a homework. It's a tricky question. Please don't make mistake. Question number 50. Question number 50 will be a homework. Do it carefully. Split each steps and write the steps properly and let me know what the answer is. Okay. Okay, so the question is A plus B gives 3C. Rate constant is K1. And 2C plus D gives P, rate constant is K2. These are the steps. Only this much is given. You have to find the total order of reaction. Option A cannot be determined. Option B, 0, C1, D2. Try it out. It's a beautiful question. Don't make mistakes. Slightly tricky. Don't make mistakes. Understand that you have coefficients over here and don't miss them out. Okay, so try it on your own. We'll be solving this in the next session. And that's all for today. We have come to the end of approximations. As you saw, there are many questions that has been asked and you will get plenty of questions in the assignment as well. Pay attention and ask questions if you have any. Okay, there'll be one more session from part 2. 1 or 2. Yeah, so we'll be discussing about Arrhenius equations in the next session and that's all. Okay, so bye-bye.